Hi, everyone. Thank you all for coming. It looks like we're not going to get more students, so we're just going to start. I'm Miriam, for you who don't know me.
Yeah, I'm George. Hope you guys are having a good week so far.
Okay, so the way we have the structures, we're structured. We did like few review questions that we're going to go over together, and then we're gonna open it for you guys if you have any more questions. All right, let's start. Oh, all right, here we go. So this question one, going to give you like a couple minutes for you to think about it and have an answer. And then if you want to unmute yourself and talk about it or just type in the chat, both are totally fine. Yes, Gianna, do you want to say why you think 2P is a primary structure? Yes, exactly. It's because they're linked by the peptide bonds, and peptide bonds are covalent bonds. And covalent bonds are usually the strongest type of bonds. So it doesn't really get denatured. When we talk about like the pH level in the environment and how it affects the protein structure, we're gonna talk more about how the primary structure does not get affected because it's covalently bonded. All right, great. Let's go to the next question. Or first, does anyone have questions about this one or need more explanation about it? If we're all good, just give thumbs up or type in the chat. Okay, great. Question two. I know it's hard to see what you guys draw since we're not in person, but if you just can draw it for yourself, and if someone wanna explain what Z did, that would be great. And I will give you another like few minutes. And then we will talk about it. Okay, if you guys are done, please just give me a thumbs up. Okay, do we need a few more minutes? Okay, I'm just gonna go over it. So the reaction that involves like making a peptide bond, that's a condensation reaction, dehydration reaction. And we get like our water forming through the reaction, like the hydrogen comes with the hydroxyl and they form a water, and then the peptide bonds forms between the alpha amine and the carbon of the carboxylic acid. And does anyone have a question about like how to realize a peptide bond in a structure? Okay. And again, why it matters that the primary structure is formed by peptide bonds, because again, we're gonna discuss later, I think, is it in the first unit? Yeah, yeah, like probably next week or the week after, we're gonna discuss the environmental factors, so pH, heat, and we're gonna discuss how these affect each level of like protein structures. And we usually, when we talk about it, we're gonna talk about how it affects like secondary, tertiary, and quaternary structures. The primary is not affected since it's covalent bonds and it's so strong, so it's usually just remains intact. Does anyone have any questions? Okay, let's go to the next question. I'm gonna give you guys again 2 minutes or so, and please just let me know when you're done with the thumbs up or type in the chat. And if someone has an answer, again, you can unmute yourself or type it in the chat. It will be great if you guys can interact. Do you guys need any help doing this one, or are you good in just taking a little bit?
Do you mind going over this one? I wasn't here during the last lecture, so I'm not sure if like that's what you guys went over.
Yeah, that's totally fine. We can go over it together.
Yeah.
So it's saying that it's asking what amino acid would possibly form a bond with positively charged R group. The positively charged R groups in the amino acids, we have 3. These are the 3 basic amino acids. Lysine, histidine, and arginine. These are the ones that have amine groups in their R group. And usually the amine groups are the ones that have a positive charge. So what do you think when we talk about, like, we know the opposite attract, right? So which amino acid would you think would form the best bond or have a good interaction with like a lysine or a histidine or an arginine, like amino acid with an amine group. Yes, Carla, do you wanna say why do you think it's aspartic acid? Or
Because its ASP is has a negative charge on it, and it's probably gonna like have some electrostatic attractions with the positively charged R group, and it may form an ionic bond.
yes, exactly. What other amino acids do you think could form a bond with like glycine? Okay, we could have also
Glutamic acid.
yeah, exactly. And it would form the same type of bond. It would form an ionic bond. We could also have another amino acid from just a polar uncharged group, and that would form what type of electrostatic interaction? It would form an ion dipole, right? Because the polar uncharged amino acids just have like a partial charge. And when they interact with, let's say, histidine, which has like a positive full charge, then it would create an ion dipole, right? We have an ion interacting with a partially charged molecule. Do you guys have any more questions about this one? Okay, let's go to the next one. And I'm gonna give you guys again a couple minutes or so, and when you're done, feel free to just unmute yourself and talk about it. Or if you would prefer to type in the chat. All right, are we ready to talk about it? Thumbs up if we are. Okay, it looks like Kenny is all set. Carla, are you done or do you need more time?
I'm done.
Okay, does one of you want to talk or share their answer? What do we think? What type of bond would happen between these two amino acids?
Is it ion dipole?
Why do you think it would be ion dipole?
Because in the aspartic acid, there's like a negative charge on the oxygen, and like one interaction with the dipole on the OH with the threonine.
Okay, so actually the asparagine, if I'm not mistaken, this one is one of the polar amino acids, not the acidic amino acid.
Oh, I thought it was aspartic.
Yeah,
my
I know,
bad.
I get confused too. There's like glutamine and asparagine, and there's glutamic acid and aspartic acid. So the names are very similar. But both the asparagine and the threonines, they're both in the polar amino acid group. So they both have partial charges. So what do you think? What type of bonds would you think will form?
So are they gonna form hydrogen bonding?
Yes, exactly. They would form a dipole bond, and hydrogen bonding is a subtype of the dipole. And
Mhm.
like you said, it would form between the hydrogen of the amine group of asparagine and the oxygen of the hydroxyl group and the other one. Great. All right, and here is just the answer if you guys just want to take a look at it. And it's also good to remember that we always have dispersion forces. Okay, does anyone have any more questions about this one? Okay, let's move on. And this one is related to the previous one. I'm gonna give you guys like a minute for that one, and just let me know when you're done with the thumbs up and we can talk about it. Okay, Carla, are you all set?
So it's valine with threonine.
Yes.
Are they gonna form van der Waals attractions?
Yeah, it's exactly. You're all there. That would be the only type of interaction. It's going to be just transient. But how would that affect like the protein structure if we change asparagine, which is polar, with valine, which is a non-polar amino acids? What effect would this have on the protein structure?
Well, van der Waals are much weaker than hydrogen bonding.
Yeah.
So I think maybe like the strength or the rigidity of the protein itself might be a little weaker.
Yeah, exactly. That would cause like a disruption on the structure because we change like a polar amino acid with a completely different amino acids from like a different group. But let's say if we change asparagine to like glutamine, then nothing really is going to happen to the protein structure because we're going to have the same type of interaction happening. So you're right, it's going to become weaker or disrupted with that type of change.
Mhm.
Okay, great. And that's question 6, and I'm gonna give you like a couple minutes just to read it and answer it, and then let me know when you're done. Just unmute yourself and we can talk about it. Okay, Carla, do you need more time? It's okay.
I'm having trouble with that question.
Okay, that's fine. We can go over it. Okay, so it's asking why do you think like the smallest or the shortest helices is like 6 amino acids, right? So let's see. So when I don't know if in the videos in class, Laura talked about how the bonds, the hydrogen bonds of like the alpha helix
Mhm.
happen every 4 amino acids, right? So we have like amino acid number 4, let's say that's whatever amino acid, and we have the alpha amino group makes a hydrogen bond with the alpha carboxyl group in like the 4th amino acid. And then we have amino acid number 2 forms the hydrogen bond with the 4th amino acids away, which is going to be amino acid number 6. So that's why the shortest one we would have would be made of 6 amino acids. That way we could at least have 2 hydrogen bonds stabilizing the secondary structure of that protein. Does that make sense?
Yeah.
Okay, do you have any more questions or need any more clarification on that one?
Yeah, I'm fine. Yeah. Thanks.
You're welcome. Okay, let's go to the next one. In this one, just asking what type of interaction would you think will happen between every 2 of these 2 amino acids? And I have this picture right here. I don't know if it's clear enough.
It's okay. I'm pulling the thing up on my computer, so it's fine.
Okay, that's great.
So I said for A,
Mhm.
I said ion dipole, and for B, I said van der Waals, and for C, I said an ionic bond, and for D, I said hydrogen bonding.
Great. That's perfect. So for the first one, you said it's going to be an ion dipole.
hmm
Do you want to talk about why, or do you want me to talk about why?
I'm just finding them on
Yeah, that's fine. Sorry, I feel like I'm
Glutamine.
on the spot, but
the and glutamate. Okay, so glutamine is polar, and it's gonna have that dipole on the oxygen, and it's gonna attract that negative charge on the oxygen in the glutamic acid
okay, so
to
you're
form an ion dipole.
yeah, you're close. You're close. It's really good. So you said that the glutamine has you notice that it has both the oxygen and the amine.
Mhm.
So it's actually like an amide group. I know you're taking Org 1 right now. So you probably didn't learn yet about the functional groups. But let's just
Yeah.
talk about the amine of this group. So it would actually have the bonds that would happen between the amine of the glutamine group and the oxygen of the glutamic acid R group. And that's how we're gonna have like an ion dipole, because the oxygen is fully charged, has a full charge. So it's an ion. That's the one in glutamic acid. And then the hydrogen or the nitrogen, like the amine group, would have like a partially
Oh, a partial positive charge. Oh, got it.
and opposite attract. So that's where the bond will happen.
Mhm.
And then for B, you said it's going to be van der Waals, right?
Mhm.
Okay, and
Because they're both like non-polar and they have like the carbon hydrogen chains.
yes, exactly. So they would only have a transient partial charges that happen for just a bit of like time, just a transient time, and then it will go away. And then you said for aspartic acid and lysine, they would have an ionic,
Ionic. Mhm.
yes. And do you want to talk about why is that?
Okay, aspartic and lysine. So, aspartic has like a negative charge on the oxygen, not of the carboxyl, the
Yeah.
other one. And the lysine has a positive charge on the NH3, and they would just like attract each other because opposites
Exactly.
attract.
Yes, and it's an ionic bond because both groups have a full charge. So we know they're
Mhm.
both ions. That's why they would form a complete ionic bond.
Yeah, would be like the electrostatic attractions, I think.
Yes, so electrostatic attractions are that's like the type of interactions that include ionic bonds, hydrogen bonds, other dipole bonds, and van der Waals.
So
It
electrostatic attractions are not just for the charged ones.
no, I mean in the contents that class, George, is it just I don't know if Laura just said.
I don't think so, no.
Okay, yeah, it's the electrostatic interactions are just all the other types of interactions other than covalent bonds.
Got it.
Perfect. And I'm just gonna talk about the last one, serine and glutamine. They're both polar amino acids, and they both have like partial charges. So serine has like a partial negative charge, and glutamine would have a partial positive charge, and that would just make a dipole interaction, or like a hydrogen bond interaction. All right, let's go to the next question. And after the next question, George will lead the rest. So I'm gonna give you a couple minutes and let me know just like you did before, and we'll talk about it.
I have a question.
Yes, go ahead.
So is how long is the protein itself?
Oh, great,
'Cause
great
it
question.
doesn't say.
Yeah, that's a great question. That's the trick in that question, actually. So it depends on how long the chain is, right? Because let's say the chain is made only of like 6 amino acids. If it's only made of 6 amino acids, where do you think the 6th amino acid would
It's gonna
be?
be closer to the C terminus because like the C terminus marks like the end of the protein.
Exactly. And where do you think would be closer to if it's 100 like amino acid chain?
It's gonna be closer to the N terminus because it's the beginning.
Yes, exactly. So that's the whole point of actually the question, so that like you realize or ask yourself how long the chain is going to be. And like if you had got a question like this in the exam, just Laura would just want to see that you see or realize that like this information is missing from the question, and then you explain your answers
Oh, okay. So
like both
okay, got it.
both ways. Yeah. So great job. And that's the answer right here. Just and now George is going to do the question. So I'm just gonna use myself.
Yep, hello. So first question, there's a amino acid chart here. Yep, so there's a glutamic acid amino acid. Yeah, glutamic acid amino acid, and it's changed, but a protein is still fully functional. So from order from least likely to most likely, which of the following do you think replace glutamic acid? And you can take a few minutes. You have an answer, or would you like me to go over it?
I know that the most likely one would be the aspartic acid, but I'm having trouble like with the other ones, like where to put them.
Okay, do you know like which type of bonds are the strongest?
Hydrogen bonding are probably the strongest after covalent.
Uh, hmm, oh, okay, we can just go over it. Can you hit the next slide? So you were right. Aspartic acid is the most likely one, but it's the most similar to glutamic acid in structure. And we know that glutamic acid is it's charged, negatively charged, same as aspartic acid, which is why it's the most likely one. And then glutamine is also very similar to glutamic acid in structure, except it's not charged. So if the protein was still fully functional, then glutamine would be second most likely. And then serine and cysteine, serine is polar, and polar would be able to do better in a glutamic acid spot than something like cysteine, which is non-polar. And the more down you go here, the harder it is for the protein to still be functional. So that's why this is the answer. Do you have any questions about it, or anything you want me to go over?
Why is glutamine in this case like better than serine?
Oh, so can you go back to the last slide? So glutamine is if you look at the structure of the amino acid, glutamine is more similar to glutamic acid than serine, which is why it would be more likely. And I didn't include it, but there's like a chart that says like how hydrophobic, like there's a like goes from hydrophobic to or most least hydrophobic to most hydrophilic. And I'm pretty sure glutamine is closer to glutamic acid than serine. Oh, I don't have it on me right now. Does that answer the question?
Yeah, thanks.
Yep, okay. Yep, and this one's similar, except now it's a phenylalanine instead of glutamic acid. Yep, let me know if you need any help or if you have an answer.
I said from most likely to least likely, or I can say it the opposite.
Yeah, you can do
Histidine,
whatever you want. Mm-hmm. Go
tyrosine,
ahead.
alanine, and then leucine.
Okay, go to the next slide.
No, I switched them. Switched all of them.
Yeah, it's okay. Yep. So basically, this time instead of going off of like polarity, we're going off of like how similar the structures are instead. Can you go back to the last slide? Oh, that's next slide. Yep. So you can see like the phenylalanine, it has a, a ring at the very end of it. So if you replace it, so we just want to replace it with something similar. So in this case, like alanine, tyrosine, leucine are all nonpolar. Histidine is the very last one, which you probably already know why. So tyrosine is the most likely one because it's very similar to the phenylalanine in structure, except for the OH group at the very end. And then leucine and alanine, leucine is bigger than alanine, and that's basically the only reason why leucine is ahead of alanine. And then that's why the answer is what the answer is. Yep, does that make any sense?
Yeah.
Okay,
So
cool.
you based it off like structure more than like polarity.
Yep, because there's like these structures you like take physical space. So you might see like on the exam or later in the unit, but it is important to keep in mind like the size of the structures.
Are we gonna have that table in the exam?
Yeah, you'll have a similar table. I think the one that Maryam used on like question 4 or something.
Yeah.
Yeah, you'll have this table, I'm pretty sure. So you don't need to memorize the amino acids, don't worry.
Good.
No, question 11. So now this is just asking how it would change each level of structures like primary structure, secondary structure, tertiary, and quaternary. Yep. Let me know once you're ready.
is it gonna be just the primary structure? But like both of them are negatively charged, so I'm thinking that like like any change would affect like the primary structure.
Yeah, that's exactly right. Oh, could you go to the next slide? Yeah, so primary structure is the only one that's changed. And that's because like the primary structure is defined as like the amino acid sequence. So any change in the amino acid sequence will change the primary structure. And it is a little counterintuitive, because you would think like a change in the primary structure would change all other structures because it's primary. But because in this case, the mutation was like to another amino acid that was very similar chemically and in terms of size, there's like pretty much minimal changes in the secondary, tertiary, and quaternary structure. So you were exactly right. Good job. Yep, so question 12. There's a cysteine, it's making some stabilizing interaction with another amino acid. And of these choices, which interactions do you think it's making? Yep, and you can let me know when you're ready.
I know that like I'm not really like quite getting the question, but I know that the disulfide bond like really stabilizes the protein because it's essentially like as strong as like a covalent bond. And I know it only happens between two cysteines.
Yep, that's right. So the question was just asking like what bonds could the cysteine be making with our amino acid. And you do the next slide. Yep. So it's just the disulfide bonds and then London dispersion forces. So two cysteines can make disulfide bonds that are covalent, like you said. And then since it's nonpolar, it can make some pretty strong London dispersion forces too, or relatively nonpolar. Yep, so you're right. Good job. Yep. Question 13. If two proteins have the same domain in their structure, that's a typo. Can we infer that they have the same primary structure? And how about their function? Yep. And you can let me know once you're ready.
Can you go straight to the answer for that one? Because I'm confused between a domain and a subunit.
Yep, okay, that's fine. Yep, so we can't infer that they have the same primary structure because since they have the same domain, it means only that part of the protein is the same, like inside the domain. That's why you can't like say that they have the same primary structure overall. And it's the same with the function because we don't know how similar they are outside of the domain. Then I do go over the subunit and like the difference between a subunit and domain in the next question. Can you hit the next slide?
Mhm.
So this one is asking if a protein has multiple domains, does that mean to have quaternary structure? Do you want me to just like go over this one?
Yeah, please.
Yep. So it doesn't mean they have quaternary structure. So quaternary structure is just like a protein with a bunch of subunits, or not subunits, but a bunch of polypeptides. So a single polypeptide can have multiple domains. And this protein could have tertiary structure. So one polypeptide could have like a lot of domains. Like a subunit is different. If there are like multiple subunits, that means there are multiple polypeptides, and that's separate from domains. So one subunit can have many different domains in it. So domains are within subunits, and that's what you should remember. Does that make sense, or do you want me to explain again?
Can you repeat that? I'm sorry.
Oh, so just the main difference between like subunits and domains is that subunits are like sort of higher order, as in one subunit can have a lot of domains inside of it. That's like the main difference. Does that make sense?
Yeah, got it. Thanks.
Okay, cool. We just have one more question. Yep. So just can you explain chemically what happens when you cook an egg? And explain to me the level of structure and and how different types of molecules interact with each other. And let me know if you're ready or if you want to just skip to the answer.
Can you, well, I know it's definitely like things happen to the primary structure, but like, does any denaturate, denaturation, I think I said it right, happen to the protein itself?
Yeah. Do you know like what type of bonds like break against heat versus like the bonds that don't?
Well, van der Waals are the weakest.
Yep.
Maybe ionic hydrogen bonding. I don't know about covalent bonds because they're pretty strong, so I'm not sure
Yeah,
about that
that's
one.
right. Yeah. So covalent bonds are like the strongest, and they're the only ones that wouldn't break in this case.
Got it.
So if you know that, do you think or what structures do you think will like do you think the primary structure will be okay, or do you think it'll be broken?
I think it's gonna be affected, yeah.
Affected?
hmm
Uh, you know what type of bonds hold together the primary structure? So
Oh,
just the
wait,
amino
no.
acid
So the
sequence.
primary structure won't be affected because it has the covalent
Yep,
bonding.
that's
So
right.
it's gonna be the secondary, tertiary, and quaternary.
Yep, that's right. Can you move to the next slide? Yeah. So what happens is like you said, the primary structure is made of covalent bonds, so they're the only ones that survive. But like the rest of it, like secondary structures, tertiary structures, quaternary structures are all like primarily like hydrogen bonds, which won't survive and they'll break apart. And then once the protein like denatures, like you said, like after that, the R groups are hydrophobic will be exposed, and then because the hydrophobia effect, they'll just come together and coagulate. That's why an egg is solid after you cook it and not like it was before when it was raw. And then that's did you have any more questions about that, or does that make sense?
Makes sense. Thanks.
Yeah, cool. So that's all the questions. If you have any questions like about the problem set or about the class in general, feel free to ask.
I do have a question about the problem set. Um,
Yeah, you can start
Let me
recording.
pull it up. Sorry,
It's okay.
give me a second.